In this video, we start off with an example. It simply says, show that this transformation is A, 1-to-1, but B, not an isometry. Okay, so just for simplicity, let's do a real simple mapping here. Let's just say that f of 0, 0, let's figure out what f of 0, 0 is. So this means x, that's x, and that's y. So we're looking for x prime, y prime over here on the other side. What does 0, 0 get mapped to? Well, if x is a 0 and y is a 0, what would x prime and y prime be? Well, x prime is 4 times 0, so x prime is going to be 0. Y prime is going to get mapped to, let's see, y is a 0, 0 plus 5, which is 5. So this mapping, just as one example, maps the origin 0, 0 to the ordered pair 0, 5. Okay, let's look at A. Let's show that it is 1-to-1. Let W be any ordered pair in the plane. We'll call it x1, y1. We'll let Z be x2, y2. Any generic ordered pair in the plane. To prove that it's 1-to-1, we will show that, let's see if you remember what to fill in here. Let's say we've got one plane here and we're mapping into this plane. Say we have W here, Z here. If f of W is equal to f of Z, in other words, they get mapped to the same point, what does that mean if this is 1-to-1? That means W has to be equal to Z. So basically squeeze them together. The only way it can happen if it's a 1-to-1 function is if W and Z are the same point. That's the only way they can get mapped to, let's see, f of W equals f of Z. Okay, so we will show that f of W equals f of Z implies that W is equal to Z. And this is just going to be very easy arithmetic to do. If f of W is equal to Z, f of Z, well, that means that f of, let's see, f of, what is f of W? F of, I guess I could call it, if I wanted to, x1 prime, y1 prime. But I think what I'm going to do is simplify that. If f of W is equal to f of Z, then f of W is going to be 4x, comma, it's going to be 4x1, and y prime is going to be y1 plus 5. This is f of W. Is equal to, and then what's f of Z? Well, it's going to look very similar. F of Z, Z is x2, y2. So to get the primes associated with that, x2, y2 is going to be 4x2, because the x prime comes from multiplying the x by 4. And then we're going to add 5 to the y value. We're going to get y2 plus 5. Well, what does that mean? That means that if these two are equal, it means the ordered pairs are equal. It means the two first terms are equal and the second terms are equal. So that means or implies that 4x1 equals 4x2. Dividing both sides by 4 gives you x1 equals x2. And likewise, we know that y1 plus 5 is equal to y2 plus 5. Subtract 5 from both sides and we get y1 equals y2. So if x1 is equal to x2 and y1 is equal to y2, therefore W equals Z. A very simple proof. We proved that it's 1-to-1 by proving that f of W equals f of Z implies that W is equal to Z. Okay, well, to show that it's not an isometry, we can just find one single ordered pair counterexample. I guess I need two ordered pairs because isometry means distance is preserved. So let's look at the distance from A to B here. Distance from A to B. We'll just picture that point, the origin, and 0, 1. How far apart are they? What's the distance from A to B? That's trivial. You can just picture it there. It's exactly 1 above the origin. Okay, now let's look at the distance from A prime to B prime and see if it's preserved. Let's see if it's also a 1. Well, what is f of A? We already did that. F of 0, 0 is 0, 5. So this would be the distance from the ordered pairs 0, 5 to what do we get when we plug in a 0, 1 into F? If X is a 0, we get out a 0. If Y is a 1, we get out 0, 6. Yeah. So that would be 0, 6. What is the distance from 0, 5 to 0, 6? 0, 6 is exactly 1 unit directly above 0, 5. So that's equal to 1. So check, check, they're equal. So that is not a counterexample. For that example, it worked. But it doesn't work for most ordered pairs of ordered pairs, it's going to fail. Here we go. Let's consider this. Let's consider C and D, where C is the origin. So we know that the distance from C to D is what? What is the distance from 0, 0 to 1, 0? Well, that's exactly 1 unit to the right. So we know without having to use the distance formula that that's just a 1. But the distance from C prime to D prime is what? Well, that's going to be the distance from, what's C prime? Okay, so C is 0, 0. If we plug in 0, 0, we get 0, 5. Is that correct? Yeah. That's C prime. And then what's D prime? When we plug in a 1 for X and a 0 for Y, we'll get out 4, 5. What is the distance from 0, 5 to 4, 5? Even without using we don't need the distance formula. You could just look at the XY plane and graph them. And that distance is 4. So, is 1 equal to 4? No, it's not. Therefore, we found a counterexample, 2 points that are distance apart 1 in the plane, but when we apply the function, the transformation, the C prime and D prime end up being 4 apart, so the distance was not preserved. Okay, number 8. This is kind of a definition. Given a triangle ABC in the plane, which I have right here, and it doesn't have to be a triangle, it could have been a square or something, some other polygon like that. The counterclockwise direction is considered to be the positive direction. So, for example, if I were going to rotate this like this, where we're going in the counterclockwise direction, that would be considered a positive orientation or a positive rotation. So the direction is positive when you're going counterclockwise, and if you go clockwise, it's negative. That's the negative orientation. So ABC, if we go in this order from here A to B to C, what direction is this? A, B, C, that is clockwise, right? So it's negative. I'll put clockwise underneath it. But if we go A to C to B, notice how we're traveling in this direction, counterclockwise. That's going to be the positive direction, counterclockwise. Okay. Number 9 says if we have a linear transformation in the plane, it is blank if it preserves the orientation of each triangle. Okay, so if it's like this, you know, if you go clockwise, it goes A, B, C. Well, if the transformation says clockwise still goes in that direction, A, B, C, then you are preserving the orientation. A linear transformation in the plane is direct if it maintains or preserves the orientation of each triangle. And its opposite if it reverses the orientation of each triangle. Okay. Number 10. The product or the composition of two transformations, call them G and F. You could just put them next to each other like they're being multiplied, or this composition is, you remember the definition of the composition? It's G of F of the point. So GF of P is the same as GF of P is the same as G composed with F of P, or G of F of P. That's the composition for all points in the plane. That's just the definition. Sometimes we usually use the word composition, but it also means product. You can use either term. All right, well, let's do that. Let's do an example of composition. Find the coordinate equation for G of F, or G composed with F, given that F is defined this way and G is defined this way. I want to know what G of F is. All right, so let's write down what F is when you operate on an ordered pair. Here's F. F of xy is going to be x prime, y prime, right? But what is x prime, y prime? Maybe I'll write it down, x prime, y prime. But they happen to be y, comma 2x. Okay, so f of xy is y 2x. Okay, so y being the first component, 2x being the second component. What is g of f of x? That's what we're looking for, g composed with f. G of f. G of f of xy. That's a little hard to read. Let me start over. G of f of xy. Well, the first step we do is just substitution. What is f of xy? What do we have on the inside here? F of xy is this. It's g of y comma 2x. Sorry for these scribbles. Let's just simplify this now. What does g do to an ordered pair? Okay, so this is really acting like x prime, y prime. And we need to find out x double prime, y double prime. Okay, so we need to plug. This is my x prime, y prime. We're plugging it into here to figure out what the x value is. It's 5 times the first one plus 2 times the second component. All right, so again, this is like my x prime, y prime. And now we need to get x double prime, y double prime. So 5 times the first one is 5y, plus 2 times the second one. What is 2 times 2x? That'd be plus 4x. Okay, and then we need to do the same to get, that's like my x double prime. Now we need to get the y double prime, and we'll be done. Okay, so it's 4 times the first one plus 3 times the second component. 4 times y gives me 4y. Plus 3 times the second component. The second component is 2x, so that's going to be plus 6x. Okay, so how do we get the x double prime? It's exactly this, 5y plus 4x. The y double prime is 4y plus 6x. This is what we're looking for.